We're going to have a look at the differentiation of e to the f of x, ln f of x, and not only a to the f of x, but also how we derive the formula that we're going to use. The first question is y equals e to the x, find dy by dx. Well, you should know that the definition of e to the x, the reason that e is such a magical number is because when you differentiate it, you get to e to the x. If you wanted to think of this in terms of a graph, you'd have e to the x looking something like that. If you plot the gradient function of this graph, then you're going to get exactly the same thing. It is its gradient function, in other words. So if you want to find the gradient at a particular point, let's say here, then you just go up to the y-axis, and not only is this the y value associated with this x value, but this is also the gradient, so it's both the y value and the gradient. Question 2. Y equals 5 e to the x. If you differentiate this, if you've got a constant, again, it doesn't change anything. It's still a constant when you differentiate. Slightly more complicated example, question 3. Y equals 4e to the 2x plus 3. Differentiate that, we're going to leave the 4 the same. For e functions, you always leave the exact e function alone. So just write down your constant and then write down your e function, because this has to feature in your derivative. Now we're going to use the chain rule. So we're going to times by the derivative of this power. If we differentiate the power, we're just going to get a 2 here. That 3 will disappear because it's only a constant. So that's going to equal 8e to the 2x plus 3. So here again, just to emphasise, the original function always appears in the derivative. So here's e to the x, here's e to the x, here's 5e to the x, here's 5e to the x, here's e to the 2x plus 3, here's e to the 2x plus 3. Your constant might change, but you're always going to get that same e function back. So just go ahead and write that e function out straight away before you do anything else. So the constant will stay the same, the e function is going to stay the same. So we're going to write that out. And then we're just going to remind ourselves, but hang on, I'm differentiating, I have to use the chain rule. Let me times by the derivative of this power. So if I times by the derivative of the power, well, this 3 would multiply by the 4, that's going to give me 12x squared. 2 times 6 is going to be 12x. And that 5, well, that's you can think of it as an x to the power 0. Bring the 0 down, you're going to get 0 times 5, which is 0. It's going to disappear. Let's bring out a 12, so we're going to get 48. And actually I could have taken an x out also of those brackets. Fifth example, we've got two functions here, so we're going to use the product rule. So let's first of all differentiate our first product, so that's going to be the x. Differentiate that, we're going to get 1. Leave the other term alone. Plus, let's leave this term alone now. And let's differentiate our second function. So differentiate e to the x squared. Well, I know, let me just put it in big brackets. I know that I've got to leave it alone, first of all, and then I'm going to use the chain rule and times by the derivative of the power, which is 2x. Let's simplify that. I'm going to simplify and also take out an e to the x squared. So e to the x squared, I'll use big square brackets. So I'm factorising. I times the first term by 1, and the second term, well, there's an x and there's a 2x, so that's going to be a 2x squared. Okay, let's look at the differentiation of ln of f of x, ln of some function. If y equals ln of f of x, then dy by dx equals the derivative of f of x over f of x. Let's see what this means. So, for example, question 1, y equals 5 ln x. To differentiate, we're going to leave that constant the same. We're going to put 1 over whatever is inside this function, so that's x, and then we're going to times by the derivative of this function. And that's just going to give us 5 over x. Okay, slightly more complicated example. So we're going to leave the constant the same, first of all. We're going to multiply that by 1 over whatever this function is, 6x minus 1, and then we're going to multiply that by the derivative of this function. So the derivative of that function is just going to be 6. That minus 1 will disappear. This is going to give us 42 over 6x minus 1. Third example. So again, just do the same thing. Keep your constant the same. For your ln, let's put 1 over that function, so 2x cubed minus 5x, and then multiply by the derivative of this function. So we're going to bring that 3 down, multiply by the 2. We'll get 6x minus 1 from the power squared minus 5. Let me keep that in brackets so that I remember the 12 is multiplying everything. Okay, fourth example. Here we've got 2 functions multiplied by each other, 2 functions in terms of x. So e to the x is our one function, ln x is another function. We're going to have to use the product rule. So e to the x, let's first differentiate that. Differentiate e to the x, we're going to get e to the x, and then we're going to leave ln x this alone, not going to do anything to that, plus, let's now leave e to the x alone, and we're going to differentiate ln x, which is going to give us 1 over x. We can take e to the x out here. We times the first term by ln x and the second term by 1 over x. We're going to look at how to differentiate a to the x. There's a formula that we're going to use, and first of all we're going to derive that formula. First thing we're going to do is let y equal a to the x. We're now going to do a little trick. We're going to think, well, we don't know how to differentiate a to the x, but we do know how to differentiate e to the x. So what if we make it to the power e? And the way we do that is we'd use the inverse, which is ln, and then put that a to the x. This is the equivalent of timesing it by 5 and then also dividing it by 5. Multiplying by 5 and dividing by 5 are inverses. Same way e and ln is an inverse, so this is actually just they'd cancel and you'd be left with a to the x. This is something that we can differentiate. We're going to use a log rule, which means we can bring this x down like that. So we're going to have e to the x ln a. Now this looks like something we can differentiate. It looks very similar to something like e to the 2x. If we wanted to differentiate that, we'd just do e to the 2x and then multiply it by this constant. We'd use the chain rule. So likewise, this ln a, that's just a constant. It could be a 2, it could be a 3. And so when we differentiate this function, we're going to be left with the same function multiplied by the derivative of this power. If we derive 2x, we get 2. If we derive ln a times x, we get ln a, because ln a is just a constant. Now we're going to use the reverse of that log rule we just used. We're going to put that x back up. Now we've got a cancellation. This e, they're just inverses of each other, the e and the ln, so they're going to cancel out, and we're going to be left with a to the x times ln a. And this is the formula that we're going to use. So let's put this into practice. If we differentiate this, we'll get dy by dx equals, leave your exponential function alone, and then remember that you have to multiply by ln 3, whatever this constant is. For a half, we're going to do the same thing. We leave this exponential, this half to the power x alone, but then remember that we have to multiply by ln of a half. Now there's a little trick here that comes up sometimes in proofs or in exam questions, and it involves a ln of a fraction. So in the same way that we could write 1 over x, we could write that as x to the minus 1. We're going to write a half as 2 to the minus 1. So I'm going to have ln to the 2 to the minus 1. I'm going to use a log rule. I'm going to bring this power down to the front, so I could get minus a half x times ln 2. It's just another way of writing it, but all of those forms are correct. Question 3. And let's simplify this so it's a bit more familiar. Let's let y equal 3 to the power b, where we're define b to equal 4x. Well, we can differentiate this, but with respect to b, because that's what our formula allows us to do. So it says leave the exponential term alone and then multiply it by ln 3. Now, we don't want dy by db, we actually want dy by dx. So dy by dx, well, what would this be in terms of this? Well, we like that dy on the top, the numerator, if we want to think of them in terms of fractions. We don't want the db at the bottom though, so we need to cancel that out. So again, thinking in terms of fractions, if we put another db at the top, we're going to cancel it out and we'll get dx. This is also the chain rule. So we've got almost everything we need to work out dy by dx, apart from we don't have the db by dx, but we can work that out. Let's come over here and differentiate our b with respect to x, and we'll get 4. Let's substitute all of these in. We need to get 3b ln 3 multiplied by 4. Let's get rid of this b because that was just a convenience. We'll substitute it back as 4x times by 4 times by ln 3. Okay, question 4 is slightly more complicated, but we'll follow the exact same steps. So again, we'll have y equals 4. Let's get rid of that horrible power there, just call it b. Now we can differentiate with respect to b. So we'll get 4b times ln 4. Now let's just make it clear what we've done here. We've let b, where b is equal to 3x squared. So this is dy by db, but what we actually want is dy by dx. And we're going to use the chain rule here because we know we can write it in terms of db, but we just need to make sure we have all these terms. I've got my dy by db, that's here, and my db by dx, well, I can work that out. Let's substitute everything in. I'm going to get 4b ln 4 multiplied by 6x. That's this term here. Let's change back our b. And just by convention, we'll put this term first, so it's clear it's not inside the ln function. And that's our final answer.